Good afternoon, everyone. This is Paweł, Czarnul. Hopefully you can all hear me. I have the pleasure of chairing this particular session on cluster, cloud, and edge computing. So we will start now since it's 2:30. So we have three very interesting papers to be presented here. So in order to meet the deadline, the slot that we have here, I'd like to ask to keep the maximum of 20 minutes for each presentation plus questions and answers. So we will follow with questions and answers immediately after each presentation. So the first paper will be dealing with storage and querying data in the IoT environment, specifically presenting TorqueDB, a distributed query engine for data to be stored in such environment. So please start the presentation and then we'll follow with questions. Thank you.
Hello everyone, my name is Dhruv and I'm a researcher at Ericsson India. I would be presenting TorqueDB, a distributed querying engine for time series data from edge local storage. I collaborated with Prathik and Anshu under the guidance of Professor Yogesh Simmhan from the Indian Institute of Science, Bangalore. Today, I will present to you the background, TorqueDB architecture, optimizations and the experiment results. As you are all aware, Internet of Things applications are required to answer queries and make decisions within a few seconds. Since IoT utilizes resource-constrained devices for sensing, all or most of the data is sent to the cloud. However, the cloud is accessed over wide area networks, which increases the query time. Hence, computation is shifting towards fog resources like workstations and edge resources like Raspberry Pi. These devices enable low latency decision making. Of late, edge devices have also been used for distributed data storage. IoT produces time series data. Currently, applications perform centralized querying and analytics on the cloud using the existing time series databases. Centralized querying on the cloud has disadvantages of WAN variability, network, and VM costs. Hence, there is a need to leverage edge or fog resources which are in close proximity of both IoT data producers and consumers. As the key requirement is to have a distributed TSDB operating across edge and fog resources, the solution must 1. Overcome the drawbacks of existing systems that are either not lightweight or lack distributed execution, and 2. Complement file-based storage on the edge. This is important because it enables analytics on file data besides querying on the TSDB itself. We propose TorqueDB, a first of its kind system that offers a distributed execution model for time series queries over edge and fog resources. It leverages ElfStore, a distributed local storage on edge and fog devices, and InfluxDB for executing time series queries. Let me first give you a brief overview of ElfStore and InfluxDB to help you understand TorqueDB better. In the figure, we have shown edge devices that host blocks and the metadata. Each block is connected to a parent fog over a high bandwidth low latency network. As you can see, edges I1, I2, I3 and I4 are connected to fog I. The fog have maps of block locations and metadata indexing. This information is vital for metadata search on blocks and locating replicas. The fogs are interconnected and form a two-level peer-to-peer network overlay. For reliability, each block is replicated across fogs and fog partitions. InfluxDB is a TSDB optimized for rapid data ingestion and querying. The IoT time series data can be bulk loaded using the line protocol format and is stored in databases called buckets that contain tables called measurements. The table columns are either tags which are indexed or fields which can be aggregated upon. The native Flux query language supports select, project, aggregate, window aggregate, and join operations. We have used the open source InfluxDB, which does not support distributed execution. As mentioned in the beginning, TorqueDB is a distributed querying engine for time series data from edge local storage. It utilizes ElfStore for storing time series data blocks on edges and performing metadata queries on them. TorqueDB extracts common metadata fields like city, time range, and min-max aggregates from the blocks. Upon querying for this metadata on fogs, matching block replicas and their locations are returned. The coordinator fog in TorqueDB uses this information to plan the query tree. Next, TorqueDB executes the queries on distributed InfluxDB at the fogs. The blocks required for query execution are transiently loaded from edges on demand and cached for future queries. Query execution and aggregation occur across multiple levels of the query tree. Let me explain the query execution sequence. Given a Flux query from the user, coordinator A extracts query predicates from it. For a typical IoT application, this could include sensor location details, time range, value filters, and the query operations. This information is used at level 4 to launch block metadata queries at fogs A, B, and C. The fog metadata indexes are used to search for matching blocks and look up their replica locations. To further validate the identified blocks at level 3, the block metadata is retrieved from host edges A2, B1, and C1 and queried. Only blocks that match the query predicates are retained. With all this information of block replicas, their locations, and the query operator, the coordinator fog A plans the level 2 subqueries and the final aggregation query. On receiving block IDs, their source edges, and subqueries from the coordinator, fogs A and B perform parallel block fetches from the assigned edges A2 and B1 at level 2. To maximize performance and reduce time costs, the block fetch is pipelined with local InfluxDB insert. Fogs A and B wait for all required blocks from edges A2 and B1 to be ingested before executing the local InfluxDB subquery. The coordinator fog A also waits for the subquery results to arrive from fog B and its own InfluxDB instance before executing the final query. Depending on the operator, level 1 could be an aggregation or a concatenation operation. Fog A performs the final query outside the time series database and sends the result to the client. For optimal query execution, the user query is split into 4 levels. Let me explain this with an example. Suppose a user wants total dust for Geneva where dust is greater than 1000 mg per meter cube for a given time range, say 11 in the morning to midnight on 15 July 2015. In level 4, TorqueDB extracts predicates like city equal to Geneva and time range for a block metadata query on the fogs. Level 3 further filters blocks using the fetch metadata. It checks for the condition dust greater than 1000 and drops the blocks which do not have the data. This ensures that only the required data is ingested into InfluxDB for query execution. Next, different fogs fetch blocks, ingest data, and execute subqueries in parallel at level 2. Finally, TorqueDB performs aggregation at level 1 and returns the result. I will now elaborate on the first optimization, query planning. We observe that level 2 block fetch and InfluxDB insert are time costly. It can be mitigated by maximizing parallelism. First, TorqueDB load balances the reads from source edges to maximize disk and network bandwidth utilization. Next, it chooses destination fogs for these blocks using one of the 2 query planning strategies, QP1 that is partition local or QP2 that is load balancing strategy. In QP1, blocks are sent in one hop to the parent fog of an edge. In QP2, blocks are load balanced across fogs to maximize parallelism for ingestion and querying on InfluxDB. The second optimization technique is caching. Fogs maintain maps for blocks loaded in their local InfluxDB and lazily propagate them to other fogs. Thus, blocks ingested once are available for future queries. The query planner uses this information to assign blocks to fogs in which they are cached and trigger QP2 for those that are not. In the future, cache replacement strategies can also be used. The setup has 12 Raspberry Pi edges and 3 workstation fogs which form 3 partitions connected over 1 Gbps network switches. We make use of a Microsoft Azure VM for our central TSDB baseline. We use the Sense Your City dataset, which contains 19.35 million rows of ambient sensor time series data. This amounts to 3360 blocks of 1 MB data inserted into ElfStore with 3x replication. The workload has 6 types of small and large time range query templates that use project, filter, simple aggregate, complex aggregate, and window flux operators. In our experiments, we used the QP2 strategy and disabled caching by default. Our results show that small time range queries execute in less than 400 milliseconds, while large queries except project filter complete in under 600 milliseconds. The execution time is dominated by InfluxDB ingestion, querying, and data fetch from ElfStore. The turnaround times of 6 templates differ due to operation across the query types. For example, project filter takes longer due to large result sets, while filter complex aggregates performs complex aggregation operations. On the other hand, filter simple aggregate and double filter simple aggregate are faster due to simpler aggregation and additional filters. If we compare TorqueDB with centralized cloud InfluxDB, the query performance is similar for small time range, while cloud is faster for the large time range. TorqueDB has shorter execution time for project filter and project double filter queries due to parallel execution. The cloud VM CPU is faster by 19 to 147% for aggregate queries. Network latency between the edge and cloud dominates the total execution time for cloud InfluxDB. This results in performance variability in addition to network and storage costs. We did 2 major optimizations to improve TorqueDB performance. I will first discuss query planning. As mentioned earlier, partition local QP1 strategy ensures single hop data transfers to the fog, while QP2 load balances across all fogs. QP2 is up to 7.6% faster and shows benefits for queries requiring several blocks. The plots for time spent across 4 execution levels for a large query using both planning strategies is shown above. The QP1 strategy, top left, 5, 3 and 4 blocks are allotted to the fog partitions. This imbalance results in an additional 30% of total time due to prolonged L2 block fetch and InfluxDB insert. This is an avoidable delay and is eliminated in QP2. Next, we utilize caching to reduce data movement and ingestion costs. We had 0%, 20% and 50% overlap in queries. As expected, the block fetch is reduced in proportion to the increase in overlap. Interestingly, even with 0% overlap in the large query workload, blocks were used across non-identical queries. This resulted in 17% fewer block fetches compared to the non-caching version. Data storage and querying over edge devices is gaining traction. StreamSide does processing on edge devices and reuses the intermediate results. Zoho proposed caching strategies to reduce communication costs. Query rewriting was also explored for privacy-aware processing. DataFog, an edge-centric data management platform, was also studied. In this paper, we described TorqueDB, which performs distributed execution of time series data on edge and fog resources. It uses the Flux query language, which is popular in IoT domains. Our optimizations of query planning and caching show results and reduce data movement and ingestion costs. In the future, we seek to support more Flux operators and conduct large-scale experiments. I thank you all and I hope you found our work to be interesting. We would love to hear from you and will be open to taking questions now. For more cutting-edge distributed systems research, you can visit the lab website or contact my professor at the link shown here. Thank you.
Thank you very much for the presentation. So now I'd like to ask everyone to ask questions, either here at the session or on the Slack forum. So are there any questions? Let me wait a moment. Maybe someone will type in questions on the forum. If not, I will ask some questions myself. Okay, so there is one question from Maciej Malawski on the forum. Let me read it. What problems do you expect when going to larger scale of parallelism?
Hi, Paweł. Thanks for the question. So again, the experience that we tried out so far was on about 15 of these Raspberry Pi devices. But separately for just the ElfStore work, which we did last year, we've sort of scaled to even a couple of hundred edge devices and tens of fog devices. So we don't sort of see much of a challenge from the block retrieval and query side of things. But InfluxDB, we found that to not be very performant, especially when it comes to inserting a lot more blocks. And that ends up being a bit of a bottleneck. So when it comes to scaling, when we have to insert a lot more blocks into InfluxDB, let's say because of a larger time range query, there we sort of would expect the time taken for doing the insertion while the query is actually running to potentially be a bottleneck. That's why the caching plays a role in sort of mitigating that. But in general, I would say if there's going to be a lot more inserts or very broad time range queries, then scalability is likely to be a bottleneck.
Okay. Okay, there are some people typing. Okay, there is a thank you from Maciej. Any more questions from the audience? So let me ask, okay, I think there is one more question coming. Okay, while Alexander is typing, let me ask my question. So in the experiment, as far as I could see, you used three fog elements, right? So the question would be, what kind of structure, I mean the graph, you set for connecting those fogs in the case of more fogs, specifically many more fogs? How do you set it? And the other question would be, what kind of settings, maybe I missed it in the presentation, what kind of settings do you have for caching in the system?
Great. So I can sort of try to take a first stab at it, and I'll probably defer to Dhruv for some more details. He's also on the presentation. So for the fogs, all the fogs were sort of connected through a single switch within the local area network. And they were connected to the edge using a sort of, it's almost like a hierarchical topology. All fogs are at one level, and the edges are connected to the fog through a private network, potentially a switch or potentially even a Wi-Fi router. And if you had more fogs, then essentially that would essentially widen. You'll have more of these, almost like a forest of sort of trees that would be there. ElfStore itself, which is the underlying block storage that we're using, that itself has almost like a distributed hash table kind of mechanism where sort of a subset of the fogs will sort of be able to talk to each other. So that's almost like a two-level hierarchical distributed hash table that we are using. So that's sort of the topological design, but all of these are within the local area network, potentially within additional private networks within each fog itself. So can you, I don't know if that does answer the first question, Paul?
Yeah, that's okay. And the other question was related to settings for caching.
Right. So Dhruv, do you want to take the settings and how your cache was configured for the experiments?
Yeah. So about the caching. So every time a query is executed at the fog level, the list of blocks is populated at each fog. And after a period of time, so that's why we mentioned lazily propagated to other fogs. So this map will be shared with the other fog partitions, and one of them will be the coordinator fog. So it will know which all blocks are already cached at various fogs, and that will be taken into account for planning the next subsequent queries.
Okay. There is one more, thank you very much. There is one more question from Alexander on the forum, so let me read it. His question is related to the existing policies to control the limitations of the IoT devices. How do you plan to provide guarantees that an IoT device will be able to support the required storage? Do you have any policy for it?
Great, thanks a lot, Alexander. So right now, the primary data storage actually stays on ElfStore. So the whole design is that users might have their own block storage on the edge devices, such as ElfStore. And we want to retain that as much as possible so that we don't have to worry too much from the TorqueDB perspective about the storage management of the block devices. Where we do need to worry about is when we start sort of inserting it into the InfluxDB and maintaining the caches and so on. Just as an aside, in ElfStore itself, which is a block storage we rely on, that actually has various mechanisms for understanding what's the capacity of each edge device from a storage perspective. And it actually does load balancing of the blocks that you're inserting across all the edge devices. So that's discussed in more detail in the earlier paper. Given that, so our focus is more in ensuring that the capacity allocated to the InfluxDB for inserting blocks, and that is adequate. Right now, we don't have an upper bound on that, and this is actually a good point. So we might actually have to, right now the load balancing is more to ensure that the insertion time as well as the querying time is sort of uniformly managed across multiple fog devices. But in case the number of inserts are potentially going to exceed the capacity of a storage capacity of a single fog, that might be an additional constraint when you're doing a query planning and load balancing, to ensure that we don't exceed the capacity available to the InfluxDB.
Okay, so thank you very much. I will now stop the questions and we'll move to the second paper, which is entitled Distributed Computing on Networks of Mobile Devices. That is dealing specifically with presentation of Oregano, which is a framework for distributed computing on mobile devices. Specifically sets or streams of data generated on mobile networks. So let's proceed.
It is my pleasure to present to you the paper Data-Centric Distributed Computing on Networks of Mobile Devices, written by Pedro Sanches, João Silva, António Teófilo, and myself, Hervé Paulin. We are researchers from the Nova Links Research Center, hosted by Universidade Nova de Lisboa in Portugal. So more and more we use our smartphones in our everyday tasks, generating and sharing considerable amounts of data. To support our growing demands, the services running in our smartphones resort to remote centralized cloud services for storage and computing power. Although the solution is well suited for many scenarios, it is not without limitations, especially when the interest on the data is localized. Consider, for instance, the example of a birthday party where people are taking and sharing photos. And you want to set up a service that allows these people to obtain the photos taken with a given face. For that purpose, first they will have to upload all photos to the cloud, then request a facial recognition service, and then either store the results also in the cloud or download them back to the smartphone. In either case, there's a high amount of data being transferred, which incurs in high latencies, and also there's a need to configure the service in advance so that everyone may access it. For some years now, the tendency is to try to process the data closer to the source, in this case, by leveraging the resources of the smartphones to process the data they are generating. This raises some challenges, namely how to find the data to be processed, how to distribute computing, how to handle churn, and how to process data batches and data streams, challenges that are not met by the current state of the art, particularly in batches and streams. In the birthday party example, a person arriving late at the party we want to process photos that have been shared before. So, and that there's a batch of data to be processed in this request, but also there are photos that are being continuously shared, and so there's also a stream of data to process, and we want to be able to process both types of data. So for that purpose, we propose Oregano that allows for data center distributed processing on network of mobile devices. It's a peer-to-peer model where the data is processed where it is generated, and it supports both batches and streams while handling churn and providing a generic framework. So looking back to our example, we have Emily, the birthday girl, and others taking photos of each other, and they want to share these photos, but now there's no centralized service. So how to find the data, how to share and find the data? What we do is we attach tags to this data, for instance, party Emily, and then we use a data-centric storage system that we developed before, named time. Time clusters devices into what we call cells, and these cells act as virtual brokers for the tags. So there's a publish-subscribe model underneath. So for each tag, there's a cell responsible for managing the publications, the metadata of the publications and of the subscription made to that tag. So the data still resides in the devices that share them or in replicas, given that time supports replication, and all the metadata is stored in the cell. So now that we know how to find the data, we have to handle how to trigger computations. For that purpose, we propose subscriptions with computation, so a new kind of subscription that we call subC. This subscription, when matched against a publication, they trigger the execution of a service, so of a computing task at the source, so where the data was published or one of its replicas. So, given this, Emily, to invoke the service, simply has to emit one of these subscriptions with computations to the tag party Emily, asking for the face recognition service. Then all the data published with that tag will be processed, and when matches are found, Emily will be notified, and then it may choose or not to download the data. So, given this high-level overview of the system, we now want to look a little bit closer to the workflow. So we want to obtain all the photos of Emily published in Party Emily, and we begin by creating a tag where the results will be published. So we call this tag Emily result. Having this tag, we may now emit the subC. The subC has several arguments. We're going to highlight here 4. The first is the subscription's validity time interval, which may begin in the past and end in the future. So if it begins in the past, it means that data that has already been published must be processed, and what we call the batches. And then if it ends in the future, it means that data that we published in the future will also be processed, so as a stream. We also have to supply the service identifier, so the face recognition service, the arguments, in this case, Emily's face, and the result tag. The cell responsible for the tag will now act as a scheduler, and it will look at all the data that has been published with the tag party Emily and divide it into batches. So we don't process everything at once. Only after receiving the results of one batch, the client may invoke, may ask for the execution of the next. So in this case, after selecting the batch to process, the scheduler will then send computing requests to the nodes storing this data. I'll be the publisher or replica, as I said before. The computing nodes will then process the data object, in this case, the photos they were asked to process. The data may be targets of a pre-processing stage. So here we are publishing photos, but the computation is being performed over features extracted from these photos. So in this case, the pre-processing stage is where the features are extracted. It may be done eagerly every time a publication is done, or lazily only at the time of the first processing. Having processed all the photos, the computing nodes may then notify the client, in this case Emily, directly. This has a problem that Emily may not be there at the time. She may leave the network and come back later. So, to avoid missing notifications, they also may use the result tag and publish the results there. After doing this, they notify the scheduler that the task is done, and then the client may receive the results. So regarding batches and streams, so consider that we are processing batches of 10 items. This value is configurable, and we have 12 photos. So the first time we ask for the service, it will process the first 10 photos. The order is also configurable. The second time, it only has 2, so only these 2 will be processed. If data, new photos are published in the future, they will automatically trigger a computing request, so there's no notion of batch. Every time a photo is received, it automatically or instantaneously triggers the computer request. So this is where we are processing data as a stream. Regarding evaluation, we did some experiments both in real-life settings as in simulation environments. We have some results in the paper. Here I'm going to highlight only 2. The first regarding latency and scalability. So here we have charts of the photo example executing in a network of 1, 2, 3 devices. This is a homogeneous setting. We also have with more devices heterogeneous settings. And here we can see that as the number of devices increases, the part in red, which is the latency for the service, decreases. Well, we can say linearly. So it means that the system is able to distribute the computation with the increase of the devices. The part in light blue is the latency of the request. So the time it takes for the scheduler to schedule the computation and then send back. So we acknowledge that this has been done. So, and this value is roughly always the same. Here we have around 2 seconds. We also have some results regarding energy consumption. Is a chart that shows the time, the energy consumed by an operation executed continuously during 1 minute. So the bar in yellow is the device in standby, so without running Oregano. Here in red, we have the device running Oregano but doing nothing, and then in blue, we have the energy consumption for the operation executing for a minute. So here we have publications, subsys, scheduling, and computing. So we see that computing is the operation that takes most of the time, but we also can see that here we processed a lot of photos in 1 minute, and the energy consumption was only 0.44%. So this means that the service can be used for a considerable amount of time, even if it's continuously processing photos. To conclude, we presented Oregano, a novel model for distributed computing on network mobile devices, which is data-centric and supports both batches and streams. Although I have shown slides about it, it's in the paper that we support churn of all types of nodes involved in the computation requests, being the client, the scheduler, and the computing nodes. We've prototyped our solution in Android. And with this prototype, we show that the system scales with a number of devices and is also energy efficient. Regarding future work, we want to improve the load balancing of the computational tasks, taking into consideration the device's battery and CPU power, and also we want to make the systems timeouts adaptive so that the system becomes more responsive when in the presence of failures. Thank you.
Thank you very much. So as before, I'd like to encourage everyone to ask questions specifically using the forum. So,
everybody, my name is Sajibila. I'm a PhD.
Yeah, so let's wait maybe for some questions. In the meantime, I will ask one or two questions. Specifically, could you please shed some more light on handling network failures in the system? You mentioned on the last slide something about timeouts. Could you please describe it in more detail?
Oh, hi to all. As I said, in the last slide, we didn't have much time to go into details on the presentation. We support churn of all the type of nodes involved in the computation requests. In the presentation, we show how we support the churn of the client. So when the client leaves, meaning that when the underlying storage that we've developed time allows for nodes to enter and leave. So it supports persistence of data. So when the client leaves, it may then later rejoin the network and obtain the results that have been published in the tag that it has generated. Regarding the others, regarding the scheduling, we have that notion of cell. A cell is a cluster of nodes. And when we address a cell, what we do is we randomly select one of the elements of the cell. If for some reason during that interaction that node leaves, we will then contact another one. Mm-hmm. The more complicated part is the interaction between the scheduler and the computing nodes. So when the scheduler asks, the scheduler, as time supports replication, we may have several nodes that have a given item, data item, in this case, the photos. It randomly selects one of them and sends the request to that node. If during if that node does not reply, does not or notify the scheduler that it has ended the task, then the task will be rescheduled. So how do we do it? There's a heartbeat mechanism that tells informs the scheduler that the node is still alive and it's processing the data. So when that heartbeat does not occur, then there's of course a timeout in there and when the timeout is triggered, the task is rescheduled. There's also the case where when the computing node is interacting with the scheduler to send those heartbeats or to inform that the task has been successfully completed, that the node in the scheduling cell is also not there anymore. So once again, we have to select another. So there are many details that we try to explain in the paper regarding the timeouts, and we mentioned that in the future work. The timeouts are configurable, but are fixed during all the execution of the system. Meaning, so you have to wait for the timeout to be triggered in order for the task to be rescheduled or for them to resend the requests and so on. So if there are several failures, the latency will have to account for the time of the timeouts. We would like to in order to make things more responsive, to have the timeouts adapt to the network conditions, so that if the network conditions are good, the timeouts are smaller, and we may detect earlier that things have gone wrong, and otherwise, when the network conditions are not good, we take the timeouts a little bit longer in order to allow for the data to arrive. Because if the timeouts are too small, then we may have more than one node performing the same task.
Okay, thank you very much. One more quick question. On the slides with results, there are some bars. I'm assuming that those bars represent standard deviation. Is that correct?
Yes. Yes.
Okay, thank you. Thank you again. I can see that there are no questions on the forum. In that case, once again, big thank you to the speaker, and we will now move to the third paper entitled WPSP, a multi-correlated weighted policy for VM selection and migration for cloud computing. So that paper deals with migration of VMs in a cloud environment. So let's proceed.
Hi everybody, my name is Sajibila. I'm a PhD student from the University of Lleida, and we are going to present our improvements in the field of cloud computing optimization problem, presenting our paper WPSP, a multi-correlated weighted policy for VM selection and migration for cloud computing. The presentation is split into next topics. First, introduction, where we will put you in a context for the problem we are trying to solve, our intentions about how to solve the problem in the proposal, the techniques developed and how they work in policies, the scenario we performed to test our techniques against other techniques in the experimentation, the results we obtain, and finally, our thoughts about the work. The scenario we present is a cloud environment formed by a data center with hosts connected to switch and interconnected virtual machines, VMs, allocated on those hosts. The resources provided by the host are assigned dynamically to the requirements of the VMs, in our case, CPU and network. The problem we are solving is the saturation of host CPU. That is, when the requirements of the VMs surpass the capacities of their host, some VMs must be migrated to hosts that can afford them, although those migrations will spread VMs that were communicating locally. There are different policies that affect the performance of the data center, such that the initial allocation of the VMs at the startup, the host saturation policy, the turning on-off policy for load balancing, in our case is deactivated, and how the network is managed. The cases we focus and improve are the selection of the VMs on the host is marked as saturated with our weighted piston selection policy, and the allocation of the VMs with the minimum migration group technique. WPSP technique is aware of CPU and network dynamic loads. Unlike other techniques focused only on CPU and the current values, WPSP prioritizes influential VMs with high CPU correlation and low network usage. As a complement, MDG VM allocation technique will try to minimize the dispersion of the VMs to far hosts. These objectives are achieved following the next proposals. First, we develop a new network module to CloudSim, the simulator we use to conduct experimentation. That allows us more control about how the data crosses the topology, what has allowed to obtain more metrics related to network plus other metrics not present in the original simulator. Then we focused on construction of the policies observing how the metrics behave when we perform specific migrations. As commented previously, CloudSim is able to simulate a cloud data center with an excellent work on CPU management and VM migrations, but with problems with network handling. We extend CloudSim to ease us the configuration of experiments, the network module, and new metrics and techniques. Focusing on this, we present WPSP, based on the Piston correlation coefficient. This helps the technique to know the degree of causality between two time series, in our case the relation between each VM and their host. In the images we can observe an example of the data used to obtain the correlation. For each VM, its CPU and network usage is compared with its host, obtaining a value between -1 and 1, where -1 indicates inverse correlation, 0 no correlation, and 1 direct correlation. Moreover, we normalized and sort the CPU and network load for each VM to obtain their influence. For each one, we obtained the accumulated usage in the last window period. In our case, E6. Then, the normalized values are obtained applying the formula for each one. In the table, there are shown how the resources usage of a set of VMs are normalized. Finally, obtaining the H-val value for each VM, showing us the balance between CPU and network usage and the capacity to saturate their host. The remaining weight value is set to 0.5 and can be modified if the resulting values are too much or not enough spread. The decision about which VM is migrated falls on this last step. The VMs that can be migrated must be under a specific threshold, being a guarantee of that moved VM has high CPU and low network influence. The image shows the H-val position of each VM depending on the correlations and the normalizations of the CPU and network. As the previous table shown, VM0 is the best candidate to be migrated because it is the nearest H-val without surpassing the threshold. In our case, 0.65. The next flow diagram shows the general schema for the WPSP algorithm. First of all, the host saturation policy sends to the WPSP the host with the CPU issues. Then we enter on the main loop. The algorithm will move VMs until the host becomes stable. To decide which VM will be moved each time, we must calculate its H-val values, including the correlation and normalization for each VM in the host. The VM with the highest value lower than the threshold will be the selected VM. Finally, we will return to the starting point to check if the host is still saturated. Now, we know which VM must be migrated. Minimum distance group algorithm is in charge of deciding which is the destination host for each one. Hosts are clustered and ordered in ascending order by relative distance to the origin host. The host with less energy increment after allocate the VM from the distance group is selected. If no host can allocate the VM, the next nearest group is tested. If no host in the data center can allocate the VM, the migration is not performed. On the explained our algorithms, we present the other algorithms and the scenario we perform for the experimentation. The next VM selection policies are used to compare with WPSP. They are the default techniques that come with CloudSim. Random sets simply selects an arbitrary VM. Minimum migration time prioritizes VMs with few RAM. Minimum utilization selects the VM with less CPU usage. And finally, maximum correlation applies a linear regression to the last 12 samples and selects the VM with the most correlated CPU in relation to the rest of the VMs. The VM allocation technique also comes with CloudSim, applying the interquality range in the last 12 samples to obtain the affordable upper threshold. If the current utilization surpasses this threshold, the host is marked as saturated. Finally, when a VM is migrated, the host that can allocate the VM and it has the best energetic performance is selected. The next tables show the VMs, hosts, traces, and network interactions you use to configure the experiment. The environment is heterogeneous to demonstrate our techniques work independently of the circumstances. CPU and network traces are equivalent to real ones. Following with the environment, the topology used is a tree shape with 16 switches, the red squares, and 36 hosts, the green circles. Further configurations are analyzed in the paper. As an example, here we can see, in another data center, how the communications between VMs, the clustered colored circles, are spread from the start of the simulation to the end. It is recommendable to maintain the VMs in the same host if it is possible to avoid intercommunications and link saturations. Before the experimentation, it is important to comment how WPSP is tuned. There are two main parameters besides width, that is set to 0.5 as explained previously. Window is a number of samples used to calculate the Pearson correlation and normalized values. In the image, we tune the window value from 2 to 30. We decided that the number between 6 and 12 offer good results. With numbers lower than 6, we obtain extreme values. On the other side, over 12, there is no improvement, and at the end, most of the values fall near 0.5. In the experimentation, we use 6. The other parameter is edge limit, set to 0.65 as shown in the algorithm section. This is a parameter that must be tuned depending on the CPU and network usage of the data center. In this case, we selected 0.65 after the drop of unassigned MIPS. The number of migrations grow linearly and the saturated data has not an important growth, so the best value according to the used metrics is 0.65. For the result section, we focus the comparison using a set of metrics obtained from the simulations. First, we present some highlights about how the combination of our techniques have a better performance. Then, a general comparative using or not MDG, and finally another comparative with all the tested metrics showing the improvement in all of them. Starting with the used bandwidth, it can be appreciated that our techniques have a high dispersion, even though our worst solution is better than the best from the others, obtaining a mean improvement of 5%. About saturated data, that is the quantity of megabits that the communication links have not been able to serve, our dispersion is similar to the others, and the improvement is substantially better, at 16% in relation to the second best technique, MMT. Continuing with the CPU consumption, there is not a big gap about saturated hosts, between 9 and 11% of improvement. However, saturation only indicates that the hosts are over 70% of its capacity, so it is correct that the technique tries to concentrate resources in less hosts. The event that really is harmful is the oversaturation, where a host cannot afford the MIPS required by its VMs. In this case, our algorithm reduces this issue in a 40% in relation to the second best techniques, MMT. The most important metric, where WPSP shines is the number of migrations, reducing in 89% the number of migrations on average. This demonstrates that WPSP migrates the most influential VMs, who really are provoking the CPU saturations. Moreover, the migrated VMs have a low impact on network, and if it is not enough, MDG will move the VMs to near host to avoid dispersion. Focusing only on MDG, it can be appreciated that independently of the VM selection policy, the technique improves all the metrics, some in a slightly way, where MDG is around 4% better than the default technique, others like unsatisfied hosts around 13%, and finally in a significant way, like the quantity of data moved due to the migrations ramming bandwidth, where MDG is around 44% better than the default technique. In the last comparative, we showed the percentage of improvement of our techniques over the other ones. In the one hand, we obtain the benefits of the WPSP due to its accurate selection of VMs, affecting directly on the number of migrations, performing more MIPS due to VMs are not migrating or they are placed in better hosts. Furthermore, WPSP does not encourage migrations of VMs with high internal communications, reducing the external traffic and hence the data saturation, obtaining an improvement of 20% in average. On the other hand, unrelated with network, VMs with important internal communications will be migrated to near hosts thanks to MDG, reducing in 89% in average the quantity of data related to migrations. After showing the results, we can conclude MDG performs better VM allocations in relation to the default VM allocation technique from CloudSim. WPSP selects correctly the most influential VMs, reducing host saturation, unsatisfied MIPS, and the dispersion of the VMs, and in combination with MDG, reducing the traffic in the data center. To conclude, among general improvements in the rest of metrics, we would like to highlight 51% less unsatisfied hosts, 20% less traffic, and 89% less migrations. The methodology used can be improved with alternative parameter tunings, topologies, and implementing more techniques. Currently, the migration cost is not penalized, so it could be interesting apply it from a real environment to obtain more realistic results. Finally, we can continue developing techniques, for example, using other kind of correlations like Spearman and Kendall. Thank you for your time, and we hope this work can help you in your research.
Thank you very much. So let's start some questions. Okay, there is a question from Maciej Malawski. How much do results depend on the workload type?
Okay, the workload type changes a lot depending on the structure of the topology, the host, the VM, so all changes. We use Planet Lab, but there are others like Materna, BitBrains, or are other kinds of workload. We want to try it, and well, the question is, it's very depending of the capacity of the VMs, the spread of the VMs, so the difference of the CPU loads. So, for example, there are, I don't know, 100 VMs that are very small, others that are very, very big, like the other 100 VMs. So depending of the experiment you create, you can take some of the small VMs or a mix of both, or only the big. So, well, it depends. You need to perform before the experimentation a test of how many CPU load you are loading in the system, and also in relation with the CPU and the network also must be balanced. So for each experiment, so you can try it, you can do any experiment, but if it's very unbalanced, so if the communications are very big in relation to the CPU, for example, So you need to balance all the algorithms, you need to change, you need to put more hosts because the system cannot afford them. So, well, yeah, it's very depending and it's a big issue I'm working.
Thank you very much. Any more questions? In the meantime, let me ask you a different question. So you are using CloudSim, right?
Yes. Yes.
Did you actually perform any kind of comparison of those simulator results against a real environment, or not really?
With other simulators, are you talking?
Yeah, so I'm assuming that you are using a simulator, right?
Yes, yes, only CloudSim, yes.
Yeah, but have you tried to actually verify results from the simulator against results from a real environment? Probably
no. Only simulators. Yeah.
Okay.
We have a little cluster in my university, but it's not enough to test this kind of experiments. So if in the day we will try it, it will be a very little topology, like 8 computers, and that's all. So for now, it's only simulation. Yes.
Okay. Thank you very much. I see no more questions on the forum, so I would like to thank you very much, especially the presenters and all the participants. So this session is now over. We now have a 30-minute break, and the parallel sessions will start again at 4 o'clock. So once again, thank you very much for participation and see you soon. Bye-bye.